So when we introduced material indices, we said that could be a single material property, or it could be a property group, such as the ratio of modulus to density. And so these are the material indices. To maximize the performance, you apply all constraints and then select the materials with the biggest index. For the case of this protective visor for motorcyclists, it could also be the case for law enforcement personnel. Something that's transparent as a visor, so optical quality, maybe it should be molded, maybe it should be light. Let's say 2 of these constraints are required. And then the objective is to make something as tough as possible. So you want to maximize fracture toughness in that case. Another objective in that particular aspect could be making something as cheap as possible. And then in that case, we choose a material with the smallest cost as opposed to one that has the highest fracture toughness. Some trade-offs might be required. And so an objective has to be contingent upon taking multiple perspectives. So Young's modulus, density, strength, these 3 individual material properties can be combined in many different ways, depending upon the loading consideration as well as the geometry of the component. So for instance, if it's a tensile tie, you want to look at strength over density. If it's a compression stress, you want E raised to half divided by rho as the material index. You take a different geometry and a different loading condition, for instance this spar beam, and you'll find out that sometimes the indices are the same even though they're completely different as geometries and loading condition. Alternatively, it could be quite different. In this case, undercarriage, which is under bending and compression, this kind of an index to the sigma y is to the power of 2 over 3 in the stadium as opposed to the airplane consideration. Suppose now the objective is to minimize the cost. So we have to take into account this material cost per kilogram of material. Again, for a tensile tie, for instance, now you go from the material index for sigma y over rho, and then in the denominator you get a cost multiple. For this completely different scenario, for this compression strut, you get a very similar material index for minimizing cost of this column over here. For the structural beam that you can see along this length, the material index gets modified in this manner. And if you're looking at the structural panel, it again gets modified in this manner, where it is sigma y to the power 0.5. So these are examples of the range of scenarios you can get with just 3 parameters over here. Let's take a single geometry compared to the multiple geometries that you saw over here. The common loading conditions include tension, bending, torsion, compression, right? Even for a constant geometry over here. So from strength of materials considerations, there are a number of ways in which you can design for that particular load direction, load condition for a given cross section. For example, for a tie rod in tension, you could indicate these 4 steps of material selection as function tie rod constraints. Say the length is specified and an axial load F should be supported by this material without failing. The objective is to minimize the mass of the tie, and the free variables include cross-sectional area and the choice of material. We have looked at this derivation earlier for this type of a tie rod. You had constraints of a specified length and a minimum load that it should be able to support without failing. M is the mass, A is the area, L is the length, rho is the density, and this is the yield strength of the material. So equation for the constraint on the area is force over area should be less than the yield strength of the material. And the objective is to minimize mass. If you keep making A smaller at some point this ratio of F over A will exceed the yield strength. So if you eliminate A, you basically express A as M divided by L times rho in this equation. If you do that and you want to minimize M, then it's a product of the load F, so it's a functional attribute, the geometry attribute, which is L, and a material attribute, which is rho over sigma y. So if you want to use a maximizing function, you maximize the reciprocal of this term, sigma y over rho. So if you plot sigma y against rho, you will be able to pick out materials that satisfy the bill. The key thing to notice is that the material index is a product of the function, the geometry, and the material. Let's take another example of this type of a product. So again, we've seen this before in the case of a beam. Right? This is a stiff beam with a mass M, area A, length L, rho, and now we are trying to deal with the stiffness, F over delta, where delta is the deflection. It can be computed from strength of materials by this term over here. Appendices will be able to give you what the constant is and what the second moment of area is. Okay. In this case, it's b to the power 4 divided by 12, because a square divided by 12, and the cross-sectional area is b square. For a beam of cross-sectional side, square beam with a cross-sectional area, b square. So you should have bending stiffness that should be less than S star, right? Stiffness should be greater than a minimum amount. So when you replace the term for the deflection delta, you will get this term. And if you replace the term for I, you will get this combination. The objective is to minimize mass, which is AL rho. And if you eliminate A in the stiffness equation and rearrange terms, you will get this seemingly complex performance metric with a material index of e to the power half divided by rho that has to be maximized in order to minimize mass. If you look closely, you have a functional relationship over here. You have a geometric consideration over here, and you have a material index consideration over here, and the product of those three end up defining the overall performance metric.